Now I'm going to solve the meteor problem that I assigned for homework. I'll first read it and then show how to solve it. A dangerous meteor flies past the Earth. It passes at a distance of 5 Earth radii from the surface of the Earth. What is the acceleration of the meteor at this distance? So let's draw the situation first, and then we'll figure out how to solve it. So let's put the Earth right here, and it's got some radius r. And then at some distance, well, if it's 5 Earth radii from the surface, then it's 6 Earth radii from the center of the Earth. So it's 6r is the distance of this meteor. Let's say it has mass m, the Earth has a mass capital M. And I want to figure out what the acceleration of the meteor is at this distance. Well, I need to use Newton's second law of motion, that the force acting on this is equal to its mass times its acceleration. Now, what's its force? Well, we can use the universal law of gravitation, gm over r squared is equal to ma. So I plugged this in and then moved this down here. The mass of the meteor cancels out, and I have the acceleration is equal to g times the mass of the Earth divided by the distance of the Earth squared. Now, there's a couple of ways that I could do this. One way I could do this is by looking up g. It's 6.67 times 10 to the minus 11th in the International System of Units. I could look up the mass of the Earth, and that's like 6 times 10 to the 24th kilograms. And then I could look up the radius of the Earth and plug in 6 Earth radii and figure out the acceleration. But there's actually a somewhat easier way to do this, and that is to realize that if this meteor was right near the surface of the Earth, I would know its acceleration would be 9.8 meters per second squared, or about 10 meters per second squared. So the acceleration near Earth, in fact right near the surface of the Earth, would have been 10 meters per second squared. So I can use that to figure out what the acceleration is when it's at a farther distance. Generally speaking, the acceleration of an object depends on the distance to the body and the mass of the body. So I can find the acceleration when it's far away compared to the acceleration when it's near. Like this, I can say this is equal to g times the mass of the Earth over the distance when it's far away squared, and compare that to g times the mass of the Earth divided by the distance to the Earth when it's near the Earth squared. The nice thing about that is the g's cancel out, the masses cancel out, and I can find the acceleration when it's far away compared to the acceleration when it's near. And by rearranging this, I have this in the denominator. So the distance when it's far and the distance when it's near, both of those are squared, so I can square this whole thing. And so when it's near compared to when it's far, this is a 1:6 ratio. So the acceleration of this meteor when it's far away compared to if it was nearby, acceleration far to acceleration near is equal to 1/36. So it's 1/36 the acceleration when it's far away compared to when it's near. And so I can figure out the acceleration when it is far away, the 6 Earth radii away, would be 10 meters per second squared, which is the acceleration it would have had if it was near the surface of the Earth, times 1/36. And I guess I can plug that into a calculator or something to figure it out. But it's about 1/40. I'll just round it off. So 1/40, so I have 10/40, or about a quarter of a meter per second squared, or right around 0.25 meters per second squared. It'd actually be a little bit bigger than that because it's a little less than 40. But you get the idea. That's how we solve this problem.